All right, today we're going to dive into one of the weirdest but most important rules in all of quantum computing, the secret of reversibility. It's an idea that pretty much flips the whole concept of calculation on its head. So let's start with something super simple. What's 1 plus 2? Right, it's 3. Easy. Our computers, our phones, everything, they do this kind of math billions of times a second. But there's a little problem hiding in this simple answer. What if I just gave you the answer 3 and asked you what numbers I started with? Well, it could have been 1 and 2. But hey, it also could have been 0 and 3. Or 3 and 0. You see the problem here? The original information is just gone, wiped out. And that problem, that loss of information, is actually at the very heart of how all classical computers work. With every single calculation, they're basically throwing away the past. And this process has a name. It's called irreversibility. So yeah, an irreversible calculation is exactly what it sounds like. You just can't work your way backwards. The output simply doesn't have enough clues to figure out what the input was. That history has been totally and permanently erased. And this is where things get really interesting because physics gets involved. There's this law called Landauer's principle, and it says that anytime you erase a bit of information, anytime you forget something, you have to generate a tiny bit of heat. It's a fundamental law of the universe. All that heat pouring out of your laptop, a huge chunk of that is literally the energy cost of forgetting. Okay, so if erasing information is such a problem, how do quantum computers get around it? Well, they follow one simple, beautiful, and absolutely non-negotiable rule. You are never, ever allowed to throw away information. Period. So how on earth do they manage to follow that rule? They do something really clever. Instead of taking two numbers, let's call them A and B, and just spitting out their sum, a quantum computer outputs the sum, A plus B, but it also carries along one of the original inputs, A. That way, the entire history is perfectly preserved. Nothing gets lost. And this amazing property is called reversibility. If you're given the output, in this case, the pair A and A plus B, you can always do the math backwards to find the exact starting inputs. There's only one possible past for every future. It's a perfect two-way street. Okay, so what's the big deal? Why is this obsession with never forgetting so important? Well, it turns out this one single rule unlocks 3 absolutely incredible abilities, things that are just impossible for regular computers. I like to call them the quantum superpowers. So these 3 superpowers are 1, the ability to run any calculation completely backwards. 2, a totally unique way to clean up leftover data called on-computing. And 3, the potential to do all this with almost zero energy waste. So first up, running a calculation backwards. I mean, think about that for a second. Because every single tiny step is reversible, you can literally build a mirror image of your quantum program to completely undo the calculation. And this isn't just some party trick. It's absolutely essential for things like Shor's algorithm, the one that can break modern encryption by basically running multiplication in reverse to find the original factors. Now for the second superpower. Remember how our quantum calculation had to keep one of the inputs around? Well, as you run more and more complex programs, you end up with a whole lot of this leftover data, this garbage. And this garbage can actually interfere with your final answer. So you need a way to clean it up, but without breaking that golden rule about never erasing anything. The solution is this genius process called uncomputing. It works in 3 steps. First, you just run the calculation, garbage and all. Second, you carefully copy the final answer, the part you actually care about, to a fresh set of quantum bits. And then step 3, and this is the magic part, you run the entire original calculation in reverse. It perfectly erases all that intermediate garbage, returning those qubits right back to their original starting state. So all you're left with is your clean input and your pure, isolated answer. It's so elegant. And finally, our third superpower takes us all the way back to that heat problem. Remember Landauer's principle? Erasing information creates heat. It's a law. So, what happens when you have a computer that, by its very nature, never erases information? You get a computer that can, in theory, run with almost no heat generation at all. And this could be a total game changer. I mean, the amount of energy that today's giant data centers consume is just astronomical. It's a huge environmental and economic cost. Reversible computing shows us a path to a future of unbelievably efficient computation, one that could slash that energy footprint. So the main takeaway here is that this one simple-sounding rule, don't use an eraser, has these profound consequences that ripple out through mathematics, through physics, and even into environmental science.
You can really see its value from all these different angles. Mathematically, it lets us run calculations in reverse, which lets us crack problems like encryption. Physically, it's the only way to preserve those delicate quantum states like superposition and interference, which is, the whole source of a quantum computer's power. And environmentally, it points the way to a future of sustainable, ultra-low power computing.
So, you see, the principle of reversibility isn't just some minor technical detail for building a better computer. It's a fundamental shift in how we even define calculation itself. It forces us to see computation not as just finding an answer and then throwing away the work, but as this perfect, reversible transformation of information. And the real question that leaves us with is, what other problems can we solve when we're forbidden from ever forgetting the question?